He said he needs to start. Yeah. Yeah. Hello, everyone. I'm really excited to be a part of this semester program. I'm Ankit Pensia, and today I will talk about some interesting directions in robust statistics that fit very nicely with sort of both of the programs here. Then I'll present one result in this thread, and then finally conclude with some broad research directions. So my talk today will focus on outliers and their impact on the training pipeline. So outliers, whether random or adversarial, contaminate all major data sets that we have. For instance, here are some examples from popular image datasets. In fact, the problem is getting increasingly worse. Modern LLM are being trained on the entire internet, and curating the dataset at such a huge scale is really difficult. In fact, the performance boost between Llama and Llama 2 was primarily attributed to the increase in quality and the quantity of training data. So we know the outliers significantly affect the performance of the trained model. And the question that we want to understand is, can we develop algorithms that are provably robust to them? So to develop robust machine learning, it turns out the central problem in this field is to develop robust mean estimation. In the problem of robust mean estimation, we are given corrupted samples from a distribution P. Here, a small fraction of samples, let's say 10% of the data, is arbitrary. And the algorithm's goal is to compute the true mean of the distribution P. As I mentioned earlier, this problem of mean estimation is central because we can sort of use it in a black box manner in a gradient descent framework and get robust machine learning out of it. So for the remainder of this talk, I'll focus mostly on the robust mean estimation. Now, I would try to give a very brief overview of the underlying principle behind all modern robust mean estimation algorithms using an example. So here is an example where our adversary has added a small fraction of samples, which has significantly affected the sample mean. Now, to curb the effect of these outliers, it is very intuitive to use what is known as trimmed means estimator, where you simply ignore the extreme quantiles and then take the sample mean. But the problem with this estimator is that when you go to higher dimensions, it is unfortunately very slow to compute. So what we actually need is an efficient signature of outliers that can be useful in high dimensions. And it turns out variance is one such signature. First, the variance can detect outliers because it's the second moment of the data, and hence it's even more sensitive to outliers than the sample mean, which is the first moment. Therefore, if the outliers are shifting the sample mean, they will be blowing up the covariance even more. And second, which is really important, is that the high variance directions are simply the leading eigenvectors of the covariance matrix, and hence they can be efficiently found. So this gives us a recipe to design robust estimation algorithms in high dimensions that is based on the higher moments. Now, with this insight and some additional steps, we can get a very simple polynomial time algorithm for robust mean estimation, where the idea is that we look for high variance directions, find outliers, remove them, and keep iterating. Now, this is a remarkable progress, but there are still huge scope of improvement. Concretely, the dream is to design robust algorithms that have similar computational requirements as that of non-robust algorithms. Or to say it differently, we want to eliminate the cost of robustness in modern machine learning. Now, some important computational metrics that we can use to judge the requirements are the following. First is the runtime, which is perhaps the most studied. And here the goal is to get linear time. Next, we have memory, which Bing-Hui also touched about. We want to develop, in this context, we want to develop robust streaming algorithms. Next, we want to see whether the robust algorithms can leverage the existing structure in the data, for example, low rank or sparsity. And finally, a big step towards widespread applicability would be to develop scalable algorithms that can sort of handle outliers in this really large ML pipelines. And in the last few years, there has been really tremendous progress in some of these topics. And I will give a flavor of this research agenda by focusing on sparse mean estimation. So to motivate the problem of sparse mean estimation, what we observe is that a lot of signals in the nature have important algebraic properties. such as low rank or sparsity, and hence it has been widely studied in statistics. So for the problem of sparse mean estimation, we are told upfront that the signal, which is mu here, has at most k non-zero entries, and k is much, much smaller than the dimension d. So think of k as polylog d. And our goal is again to estimate the true mean in the Euclidean norm. Now, this sparsity structure, partly the reason behind its popularity is that this structure significantly reduces the sample complexity from linear in the dimension d to only polylogarithmic. And this is true for both the robust version of the problem and the non-robust version of the problem. However, when we look at the runtime of the algorithms, we see a huge gap. So the existing robust algorithms use at least d square runtime. I'm hiding the dependence on the sample complexity. So I'm hiding poly factors in k and log d. So the robust algorithms needed to use at least d square runtime, while the non-robust algorithms were linear time, which were simply take the sample mean and threshold. And going back to the previous thread, what we want to understand here is that whether this runtime is there a fundamental difference between the non-robust runtime and the robust runtime? And to highlight the challenges that come up towards solving this problem, there are two main challenges. First is that we want to break this quadratic barrier at d square. But as we saw earlier, robust algorithms typically need access to higher moments of the data, which in this case is covariance matrix, and it's already quadratic in size. So we can't even write down the covariance matrix explicitly. Now, there are usual tricks in the literature where we don't have to write down the covariance matrix, but what we can do is something like power iteration, and all we need is matrix vector products. But it is known that those sort of tricks do not work for sparse eigenvectors, which is what is needed here. And overall, this leads to the following question, whether this runtime barrier of quadratic is fundamental. And towards answering this problem, the result is the following. So there is an algorithm to compute mu hat, which first of all has near optimal error. Now there is a parameter q, which it uses to trade off runtime and sample complexity. So for any q bigger than 3, what we see is that the runtime is indeed sub-quadratic, which is what we wanted. And the sample complexity is also polynomial in the factors that we wanted, which is polynomial in the sparsity parameter k and log d. So no dimension explicit dependence in the sample complexity. Okay, so I won't go into the proof details here, but the key idea here was to establish the connection between this sparse eigenvalue problem and this other problem known as light bulb problem, or the correlated detection problem. And I'll be happy to talk about it offline. Okay, so now I'll mention some of the research directions that I've been thinking about lately. So broadly, I'm interested in fundamental problems in machine learning concerning both their statistical and computational aspects. And to be more specific, I'm interested in learning algorithms that work with minimal resources. So by resources, what I mean here is both the computational and the statistical resources, which could be of limited quantity or quality. So let me elaborate it a bit more. So this is a cartoon diagram of the modern machine learning pipeline, where we have data often coming from multiple individuals, which is then fed to an algorithm, which is physically or institutionally separated from the individuals, which is then used to generate the insights. Now, the first and the foremost resource that a machine learning algorithm uses is the data, which, as we saw earlier in the talk, could be of limited quality. It could be due to outliers or the heavy tails, or let's say extreme heterogeneity, because they might be coming from different populations. Now, as I mentioned earlier, the data is coming from individuals, and the algorithm is a separate entity belonging to a different institution. And the individuals might not be comfortable with sharing their data directly with the algorithm. So this motivates us to think of privacy as a budget and sensitive information as a resource. Similarly, in this distributed pipelines, the users might have monetary cost to send their data exactly, so they need to be quantized, and we need to think of communication as a resource as well. And finally, moving on to the algorithm side, we all know that big data sets and big ML models are simply too large to fit in the memory. And streaming algorithms have a rich literature, but developing streaming algorithms that respect some of the other constraints, such as outliers and privacy, is an exciting research area. And finally, even in the idealistic setting, I'm interested in developing instance optimal algorithms as opposed to min-max optimal algorithms. And this change in viewpoint often leads to improved algorithms and understanding. So at the program, I'm really excited to learn more about and think about similar topics. For example, distribution shift, out of distribution, domain adaptation, and so on. And I'll be happy to chat more.
Thank you. Okay. Any questions?
Yes, pretty broader question connecting to the previous talk. I guess there's been a lot of work on robust algorithms for distribution. But if your goal is some classification task, then like in the previous talk, you can imagine being robust for that particular task. So do you see where that would fit in this purpose?
Right. So here I mostly focused on robust mean estimation, but you can take any supervised learning problem or unsupervised learning problem and ask a similar question: is it robust to outliers in the data? And in the last few years, there has been a really great progress on particular problems such as regression, logistic regression, clustering, and so on. So here I focused on mean estimation for simplicity, but yeah, ideally, for any learning task, we would want a robust algorithm because yeah, I wouldn't want my prediction to be really sensitive to one outlier in the training data that somehow came in.
You probably don't mean one as in one single outlier.
Right.
So that changes your estimate. But as we discussed last week briefly, I wonder, for me, from the applied side, there's often information in the outliers.
Right.
There are outliers for a reason.
Right.
Set of models. Do you have any ideas in which direction you would take that or what criteria you would use to decide whether an outlier is something to be removed or robustified against, or has information it should change your model?
Yeah, that's a really good question. And I don't have a concrete answer for that. But what I can tell you is that these algorithms that have been developed don't just output a mean estimate. What they will tell you is that take this subset, a large subset of the original data, and compute its sample mean. So in essence, it outputs a partition of what it thinks are inliers and what it thinks are outliers. So for someone who is working with the data, they will get a partition, and then they can look at the outlier set that is returned and sort of investigate it a bit more and think of it and find out whether there are, if they are, they correspond to a certain subgroup population or not. So basically the overall idea is that you don't just get one point estimate, you get something more, and perhaps that could be useful.
That's the aspect of robustness. If you bring in the aspect of privacy,
yeah, so as far as I can, right, so that's a really good question. And as far as I can tell, there is no private sparse mean estimation algorithm with optimal sample complexity that is sub-quadratic. If it were, it would have given us robustness directly, but I don't think the algorithm that we discussed here gives privacy directly. So yeah, it sort of brings in the other aspects that we want. Robustness is one, privacy is another, and we would want to minimize the computational cost of those properties that we want from our algorithm.
Is there any fundamental reason why sampling complexity has to go up if you want to faster runtime, or is that incidental?
Right, that's a really good question. So for this analysis to work, the higher sample complexity is needed. I don't know if it's fundamental or not. there has been some really interesting recent work by Kabir, Alex, and Jay, I think, where they sort of investigated information computation gaps that might arise if you sort of try to distinguish between the near linear time algorithms or quadratic runtime algorithms. They were looking at one particular model, I think in planted click for queries, but it could be possible that if you want sub-quadratic time algorithms, it has to use more samples. I don't think that's the case here, but it's possible.
For example, if you use your algorithm with 2 equals 2, you get e to the 2.1.
Yeah. So use 3 as written here.
I mean, that's the reason you wrote 3.
Yeah.
This theorem also can be adapted to
That's a really good question, and this is something I should have mentioned. So this is one progress on this topic, and there are 3 very important directions that can be pursued from just this theorem. First is, as mentioned, the algorithm really needs the inliers, not the outliers, just the inliers to be Gaussian, and it currently doesn't work for heavy tail distribution. And the precise reason is that currently we want the degree 2 polynomials to have bounded variance. That is true for Gaussians, but might not be true for other distributions. The second is to get actual linear time. It's sub-quadratic, but still far. And third is, as Abhishek said, we would want the optimal sample complexity instead of just being tight in polynomial factors.
So, thank you.